Let's solve problem 7.13 for Microelectronic Circuits 8th edition by Sedra and Smith. Designer considers a number of low voltage BJT amplifier designs utilizing power supplies with voltage VCC of all these different values. For transistors, saturate at VCE equals 0.3 volts. We'll ask a bunch of questions. So I'm going to answer all these questions first with VCC equals 1 volt, and then we'll repeat the process for these other values, but it should be pretty repetitive. So first question, what is the largest possible voltage gain achievable with the supply voltage of 1 volt? So we can use the following equation, that the gain is equal to VCC minus VCE divided by the thermal voltage. So that's going to be, for this case of 1 volt, 1 minus 0.3 divided by 0.25 volts. And that should be equal to 28 volt per volt. Okay. Next question. If in each case biasing is adjusted so that VCE equals VCC divided by 2, what gains are achieved? So we're just going to call this AV new. So now it's going to be VCC minus, so VCE is now equal to VCC divided by 2 divided by thermal voltage. So that's going to be 1 minus 1/2 divided by thermal voltage. And that'll be 20 volt per volt. Okay, I think there's one question left. If a negative going output signal swing of 0.4 volts is required, at what VCE should the transistor be biased to obtain maximum gain? Okay, so this will be the same for all cases of VCC. So if a negative output swing of 0.4 volt is required, then in order to obtain the maximum gain from the transistor, it needs to be biased at VCE equals that maximum gain, 0.4 volts, plus its peak near saturation. We don't want to leave saturation, so VCE max will be 0.3 volts in saturation. So we're going to add that. So 0.3 volts. So VCE will become 0.7 volts. And then for that value, AV will be 1 minus 0.7 divided by 0.025, which is equal to 12 volt per volt. Okay, so that's the process for all of these. Let me clean this up and we'll do the next 3 cases. Okay, so let's solve this again for VCC equals 1.5 volts. So our answer to the first question, the largest possible gain, is an appropriate label will be AV max. So that's going to be VCC 1.5 minus VCE 0.3 divided by 0.025. So that is equal to 48 volt per volt. And then for this VCC divided by 2, we will get 1.5 minus 1.5 divided by 2 is just 0.75 divided by 0.025. That's equal to 30 volt per volt. And then lastly, with this negative going signal, that would be 1.5 minus just the straight 0.7 volts again, divided by 0.025, and that is equal to 32 volt per volt. Okay, let's do VCC equals 2. So our maximum gain we can achieve will be 2 minus 0.3 divided by 0.025, and that is equal to 68 volt per volt. Now, given the second case of VCC divided by 2, we're going to get 2 minus 2 divided by 2 is just 1 divided by 0.025 equals, looks like 40 volt per volt. And then lastly, again with this last case, it's always just going to be 2 minus It's always going to be that 0.7. And that gets us 52 volt per volt. Okay, lastly, let's do VCC equals 3 volts. So our maximum gain we can achieve is going to be 3 minus 0.3 divided by 0.025, and that's equal to 108 volt per volt. Then using VCC divided by 2, that'll be 3 minus 1.5 divided by 0.025, and that's equal to 60 volt per volt. And then lastly, with the negative going signal, that's going to be 3 minus 0.7 divided by 0.025, and that's going to be 92 volt per volt. And that solves the problem. Thank you for watching my video. For any comments, questions, or video suggestions, feel free to reach me in the comment section or by email. Thank you, and have a great day.